Okay, so I'm Jonathan Stern. I'm a Sierra Fellow at the Northwestern University. And I want to talk to you today about using observations to infer the physical conditions in the CGM. And specifically, I'm going to talk about the CGM of Milky Way-like galaxies. Okay, so star-forming L-star galaxies at low redshift. And I'm going to be even more specific than that. I'm going to focus on the conditions beyond 100 kiloparsec from the galaxy. Okay, so the outer part of the CGM, beyond roughly half the virial radius of the dark matter halo. Now, the reason I'm focusing on this specific part of parameter space is because it allows us to test a very basic concept in galaxy formation theory. Okay, it allows us to infer the properties of the virial shock in halos of 10 to the 12 solar masses. Okay, so the so-called magic scale of galaxy formation. So the way I'm going to do that, I'm going to first review the observational clues that we have of gases in this region, mainly O6, H1, and dust. And then I'm going to infer the physical conditions under two assumptions: that oxygen is collisionally ionized into the O6 state, and that oxygen is photoionized by the UV background into the O6 state. Okay, I'll then connect both scenarios, okay, with the properties of virial shock, what each scenario tells us about the virial shock. And last, I'm going to end by giving predictions for each scenario for neon 8, so that will allow us to understand which one of these two scenarios is the correct scenario within a time scale of a year or so. Okay. Okay. So the observations, as discussed before me by Hummels and Drummond. Okay, so Coase-Hallis observations. I'll start with O6. Very known result. Okay, the Coase-Hallis team measured the O6 column in the CGM of low redshift galaxies. In blue galaxies, they found large O6 columns. In red galaxies, O6 is rarely detected and with lower columns. Okay, so I'm going to focus on blue galaxies where O6 are almost always detected. Okay, so this is the panel here shows you the O6 column as a function of impact parameter. I normalize the impact parameter by the virial radius of the dark matter halo. The top axis shows you the typical impact parameter in kiloparsec for the median virial radius in our sample. You can see that the O6 columns are flat, okay, up to roughly 70% of the virial radius, and they did drop pretty quickly. If we want to understand what that means in terms of the physical distance of O6, we simply need to deproject the observations. That's shown here in the lower left panel. Okay, you can see that the O6 resides at a characteristic distance of 150 kiloparsec, or roughly 2/3 of the virial radius. Okay, so what I want you to remember from this slide is that most of the O6 resides in the outer part of the halo. Okay, beyond roughly 100 kiloparsec. Second observation is H1. Okay, so this is H1 to O6 ratio as a function of impact parameter. You can see that this ratio is very large at small impact parameters with values up to 10 to the 5 from 100 10 to the 5. But when you go to large impact parameters where most of the O6 resides, okay, this ratio is much lower. It has values between 1 and 10. Okay, so this dependence on impact parameter tells us that the H1, which gives rise to these large columns, is at smaller spatial scales, okay, than the O6. Okay, at the spatial scales where you see O6, the typical H1 to O6 ratio is between 1 and 10. And the third observation I'm going to discuss is observations of dust. Okay, so the differential extinction induced by dust. This is a measurement done by Brice Menard in 2010. Essentially, he measured the mean differential extinction in background quasars as a function of impact parameter from foreground galaxies. Okay, so this is his signal. You can decompose that into a 1 halo and 2 halo term. Okay, you can see that the 1 halo term extends roughly out to the virial radius. Okay, and if you calculate the mass implied by these observations, the dust mass, you get that the dust mass is comparable to the dust mass in the disk of the galaxy. Okay, so that tells you that this signal cannot come from satellite galaxies. It's more likely in the CGM. Okay, at the distances of O6, the typical differential extinction is of the order of 10 to the minus 3. Okay, so I showed you observations of O6, H1, and dust. Okay, but there are other observations that have traditionally been used to constrain the conditions of CGM. Okay, but I want you to point out the fact that all these other observations mainly constrain the conditions in the inner part of the halo. Okay, not in the outer part, which is the focus of my talk. Okay, so low ions are typically seen only up to impact parameters of 40 or 50% of the virial radius. X-ray emission is detectable only in very nearby galaxies and only to a few tens of kiloparsecs. And also the constraints that you get from RAM pressure stripping of Milky Way satellites, that's also limited to the conditions in the inner halo, okay, because that's where most of the RAM pressure stripping is happening. Okay, so when we understand the outer part of the halo, we're really limited to O6, H1, and dust. Okay, so I showed you the observations. So let's discuss the inferred physical conditions. So the first question is, what is the ionization mechanism that gives O6? Okay, so what you see here, okay, so you see here the O6 fraction, the fraction of oxygen particles which are in the O6 state as a function of density and temperature. Okay, and I'm assuming equilibrium conditions. And you can see that O6 peaks in two distinct branches at 300,000 K, where the O6 is collisionally ionized, and at low densities and low temperature, where O6 is photoionized. Okay, photoionized by the UV background. Okay. So the most basic question we need to understand, in order to understand what the observations are telling us on the physical conditions, is what is the ionization mechanism of O6. Okay, so the first argument we can make in this respect is a pressure argument. Okay, so these diagonal lines are lines of constant pressure, okay, and they delimit the range of pressure seen in cosmological simulations. Okay, so essentially you get that from the fact that the virial shock is roughly at the virial radius, so a distance beyond the O6, okay, and hence the pressures are relatively high. Okay, now you can see that this argument is only consistent with the collisionally ionized scenario. Okay, so the photoionized O6 essentially requires pressures, gas pressures which are much, much lower than seen in simulations. Okay, it essentially requires the virial shock to be within, okay, where O6 is. Okay, at smaller distance than the O6. Okay, so this pressure argument is essentially why all simulations who looked at this problem reached the conclusion that O6 is collisionally ionized rather than photoionized. Okay, but I want you to keep your minds open, okay, and to the possibility that maybe the simulations are over predicting the pressures. Okay, so maybe O6 is indeed photoionized. Okay, a second argument that we can make is a cooling luminosity argument. Okay, so essentially we can calculate the cooling luminosity of the gas traced by O6 by finding out the mass of the gas traced by O6. All we need to do is integrate the observations and then multiplying that by the cooling function. Okay, so the cooling function is a function of density and temperature. So we get these lines. Okay, and if you compare that to our two solutions, okay, so collisionally ionized O6 comes from this region, you can see that cooling luminosity is very, very large. Okay, 10 to the 49 ergs per year. Okay, so that means, okay, that's roughly equal to the entire supernova energy production rate in the galaxy. Okay, so if you believe that O6 is collisionally ionized, okay, you have to explain this huge amount of cooling. Okay, if you calculate what's the mass flow rate in the cooling flow, you get 20 solar masses per year. Okay, so that means that you need some sorts of heating, some constant sorts of heating, because otherwise all of the halo would have cooled by now. Okay. On the other hand, the photoionized O6 solution, okay, is an equilibrium solution. Okay, essentially the cooling is balanced by heating by the UV background. Okay, so there's no net cooling. Okay. A third argument we can make is based on the observed ratio of H1 to O6 that we see in the outer halo. Okay, so what I plotted here is what is the expected ratio of H1 to O6 as a function of density and temperature. I'm assuming the H1 and O6 come from a single phase, and I'm assuming a third solar metallicity. Okay, so a third solar metallicity is essentially the lowest, it's a lower limit on the metallicity of the gas traced by O6, okay, because it's the minimum metallicity you need to reproduce a large observed columns of O6. And okay, so again, if we compare to our two solutions, so you can see that in the photoionized O6 region, we get the correct ratio of H1 to O6, okay, in the range of 1 to 10. Okay, so if O6 is photoionized, okay, it means that the H1 and O6 come from the same phase. Okay, on the other hand, in the collision ionized scenario, the amount of H1 in the gas traced by O6 is much too low to explain the observations, so we need to assume a second phase, a cooler phase, which produces the H1. Okay, so the third argument is based on the dust observations. Okay, so this is the Brice-Menard observation zoomed in on the circumgalactic medium. This is the 2 halo term. Okay, this red line, okay, is the dust in magnesium-2 absorbers. Okay, and we know how much dust there is in magnesium-2 absorbers because that's a directly observed property. So based on the magnesium-2 equivalent width, okay, we know what fraction of the Brice-Menard signal is due to magnesium-2 clouds. Okay, so that's this red line. You can see that dust in magnesium-2 clouds can reproduce the observations up to impact parameters of roughly 50 kiloparsec. Okay, so the question is, what is the gas phase associated with these observations? Okay, so I'll make a very simple assumption that there's dust in the gas traced by O6 with a standard dust to metal ratio. Okay, so if I do that, okay, I get this blue line. Okay, so this is essentially the average column of the O6 multiplied by the dust to metal ratio. And you can see that if we sum up all the observations, we get a good fit to Blitzman-Al's observations. Okay, so this is telling you that if we simply assume that there's dust in the O6 gas, okay, we can explain the differential extinction observations. So that's an interesting result. But I want you to note that this assumption only makes sense in the context of the photoionized scenario. Okay, because in the photoionized scenario, the gas traced by O6 is all the gas that we have, or it's most of the mass of the gas in the outer CGM. Okay, if we believe that O6 is collisionally ionized, okay, then the O6 is tracing only a small window of a much more massive cooling flow. Okay, in which case, if we assume that the O6 gas is dusty, okay, we have to assume that the entire cooling flow is dusty, and therefore we will clearly overpredict the differential extinction observations. Okay, so the point I want you to take from this slide, okay, is that if we assume that O6 is photoionized, we can predict the dust observations from the O6 columns. Okay, so that's a nice feature of the photoionized O6 scenario. Okay, so before I go to the predictions, I just want to show you a brief schematic of what the two scenarios mean. Okay, so essentially the scenario where O6 is collisionally ionized is the scenario seen in cosmological simulations. Okay, where the dense hot gas, the virially shocked phase, extends out to roughly the virial radius of the halo. Okay, so the shock radius is roughly at the virial radius, and the pressures are high throughout the halo. Okay, in this scenario, it means that in the outer part of the halo, there's a cooling flow, a very massive cooling flow, which creates O6, a little bit of H1, and for some reason, no low ions. Okay, so these observations still need to be explained. In the scenario I'm talking about here, okay, where O6 is photoionized, it's a very different scenario. The virial shock, okay, is essentially somewhere near half the virial radius. Okay, so the dense hot gas extends only out to half the virial radius. Beyond that, the gas pressures are much lower. Okay, and the dominant mass phase in the outer part of the halo is this cool low density phase, which has a nice property of reproducing all the observations. So the O6, H1, and dust all come from a single phase. Okay, so I'll end with predictions. So this prediction is based on the fact that density and temperature generally decrease outwards in the CGM. Okay, so in a collisionally ionized scenario where the ionization level is determined by temperature, ionization should decrease outwards. On the other hand, in a photoionized scenario, okay, where the ionization level is inverse proportional to the gas density, ionization should increase outwards. Okay, so you can see this in this plot. Okay, so this is neon 8 divided by O6. So this is based on the fire simulation. Okay, you can see that at small impact parameters, the neon 8 to O6 should decrease. And then at roughly 80% of the virial radius, there's an inflection, and this ratio should increase. Okay, and if you look at the simulation, this inflection point corresponds to the distance where the dominant ionization mechanism changes from collisional ionization to photoionization. Okay, so I remind you that most of the O6 comes from here, so this simulation suggests that O6 is mainly collisionally ionized. So essentially my prediction, or the prediction of the photoionized scenario, okay, is that this inflection point should happen at much smaller impact parameters than predicted by the simulations. Okay, so essentially this inflection point is a method to measure the distance to the virial shock in these type of galaxies. Okay, and the nice thing is that there's a planned observations of neon 8 in the upcoming HST cycle 25. Okay, so I'll just summarize, and I'll focus my summary on this alternative scenario where the O6 is photoionized by the UV background. Okay, so in this scenario, the virial shock in Milky Way-like galaxies is only at half the virial radius. And all the gas, that the pressures beyond this radius are much lower. And I think this scenario has two main advantages. So one advantage is that it can explain all the observations, the O6, the H1, and the dust, with a single gas phase. Okay, so essentially you can, based on the O6 and the assumption of photoionization, you can predict the H1 and the dust that you see. And another advantage is that this means that this gas is in equilibrium. You don't need to invoke some strong feedback to counteract the strong cooling. Of course, the main challenge of this scenario is that it means that simulations significantly over-predict the gas pressures beyond half the virial radius. Okay, and the question is why? Okay, so we've been thinking about this a lot. One possibility which we think is that maybe that the simulations are under-predicting the metallicity in the outer CGM, and therefore they're under-predicting the hot gas, the hot gas cooling, and therefore they're over-predicting the pressure. And the nice thing is that we can soon be able to resolve this question using observations of neon 8. Yep. Yep.
Non-star-friendly galaxies have big halos, but oxygen 5 not oxygen 6. If it's ionized by UV background, that's present for both star-forming and non-star-forming galaxies.
Yep.
So am I missing something?
Yeah. So I think in red galaxies. So I think in the red galaxies the simulations are right. So in the red galaxy the pressures are high out to the virial radius, and therefore you simply don't go to 06 because the pressure is too large to produce photoionized 06. No, I think it's too large. So the 06 resides at too large distances to be created by the galaxy. Essentially, the scenario I'm suggesting is what Deckel and Dillenboim talked in 2006, that in blue galaxies, okay, the halo is essentially collapsed halo, the virial shock is well within the virial radius, but in red galaxies, the halo is much more, the shock is much more stable. So it's essentially the same thing.
What are the observations looking through clusters or groups where you know that gas is high temperature and high pressure? They not see options?
Yeah, so you less in high clusters you less see 06. Yeah, I think, right? It's relatively less. So it's more like the observations of the red galaxies that you don't see 06. Yeah.
Okay. All right. Well, let's thank Jonathan.